You might think cosmology is one of those parts of science that feels settled, a map already drawn, the major continents labeled, the oceans measured, the equations polished, until they look inevitable. But I want you to pause for a moment and imagine something far less comfortable. Imagine that the map is wrong, not slightly off, not missing a coastline, but fundamentally misleading. And the first hints of that possibility did not come from philosophy or speculation. They came from data, from a telescope quietly looking deeper than any instrument before it, and reporting back something that should not exist. In January 2026, astronomers confirmed a galaxy whose light has traveled for more than 13.5 billion years, meaning we are seeing it as it appeared just 280 million years after the Big Bang, when the universe was only about 2% of its current age. And according to every model we trusted, galaxies at that time should have been faint, chaotic, chemically primitive clouds just beginning to form stars. But this one was bright, compact, structured, and chemically enriched, already showing signs of elements that normally require multiple generations of stellar evolution, as if the universe had skipped steps, as if time itself had been compressed. And the scientist leading the observations said something quietly unsettling. It looks nothing like what we expected. That sentence matters more than any number because it tells you something deeper than a measurement. It tells you that the story we thought we understood may be incomplete. And this was not an isolated anomaly, because the same telescope has now found dozens, then hundreds, of early galaxies that appear too bright, too massive, too mature, far earlier than the timeline predicted by the standard model of cosmology. And when one observation disagrees with theory, you question the observation. But when many observations disagree in the same direction, you start questioning the theory itself. At the same time, another problem had been growing quietly in the background, something that sounds technical until you realize how fundamental it is. A disagreement over how fast the universe is expanding, a number called the Hubble constant, which determines not only the size of the universe, but its age and its fate. And there are two ways to measure it. One that looks at the early universe using the cosmic microwave background, and another that measures distances to nearby galaxies and works outward. And for years, those two methods gave slightly different answers. Small enough to ignore, small enough to hope would disappear with better data. But instead, the gap widened. The early universe method giving around 67 kilometers per second per megaparsec. The local measurements giving around 73 to 76. And that difference may look trivial, but in precision cosmology it is enormous. And by 2025, the discrepancy crossed the 5 sigma threshold, the same statistical standard used to confirm the Higgs boson, which means the probability that this is a fluke is less than 1 in several million. I want you to notice what that implies, because this is not just about a number being slightly off. If the expansion rate is different depending on how you measure it, then either our understanding of the early universe is wrong, or our understanding of the late universe is wrong, or something about the physics connecting the two is missing. And none of those possibilities are comfortable, because the standard cosmological model has been remarkably successful for decades. Explaining the cosmic microwave background, large-scale structure, and the abundance of elements, it was the closest thing cosmology had to a finished framework. And now the edges of that framework are starting to fray. When I first encountered this tension, what struck me was not the mathematics, but the feeling that comes with it. The realization that even at the largest scale imaginable, the universe is still capable of surprising us, that our equations are not laws handed down from reality, but approximations we refine when reality refuses to cooperate. And there is something profoundly human about that, because it reminds you that science is not a monument. It is a conversation. And sometimes the universe answers in a way that forces you to admit you misunderstood the question. Go outside on a truly dark night, far from city lights, and look up, not casually, but with patience, letting your eyes adjust until the faintest stars begin to appear. And after a few minutes, the sky fills with thousands of points of light scattered in every direction. And it feels enormous. It feels infinite. It feels like you are staring directly into the universe itself. But you are not. And this is one of the most misleading experiences you can have. Because almost every star you can see with your naked eye lies within roughly 1,000 light years of Earth, which sounds vast until you realize the Milky Way galaxy is about 100,000 light years across, meaning that when you look up at the night sky, you are seeing about 1% of the diameter of your own galaxy. And even that 1% is sparsely populated compared to what lies beyond, since the Milky Way contains roughly 250 billion stars, and you are seeing perhaps 4,000, which is like standing in the middle of a continent, spotting a few lights on the horizon. And concluding, you have seen the whole civilization. I remember the first time I really understood this not as a number, but as a picture. Imagining myself shrinking the Milky Way down so that its entire 100,000 light-year span fit across a city, then realizing that the stars visible to the naked eye would occupy a single neighborhood, a quiet suburb with empty streets, while the rest of the city remained completely invisible. And that is just one galaxy, because the observable universe contains roughly 2 trillion galaxies, each with billions or hundreds of billions of stars. And suddenly the night sky stops being a panorama and becomes a peephole, a narrow opening through which you glimpse only your immediate surroundings. There is something deceptive about brightness that encourages the illusion, because the stars you see are the brightest and closest, the cosmic equivalent of streetlights, while the vast majority are too faint to detect, and the galaxies beyond them are invisible without telescopes. And even with telescopes, you are still sampling tiny regions of an enormous whole. And this is why the sky looks dense when it is actually sparse, because your brain fills in the gaps, turning a handful of nearby lights into a continuous dome. If you could step back far enough, if you could leave the Milky Way and look at it from outside, you would see a thin spiral disk floating in darkness, and those 4,000 visible stars would dissolve into a small cluster near one edge, and beyond the galaxy there would be more darkness, and then another galaxy millions of light years away, and another, not packed together, but separated by distances so large that even light takes millions of years to cross them. The universe is not crowded, it is overwhelmingly empty. And the illusion of fullness comes from proximity, from being embedded inside one small region and mistaking it for the whole. There is a strange shift that happens when you accept this, because the night sky stops feeling like a ceiling and starts feeling like a gap, a thin scattering of nearby lights surrounded by unimaginable distance. And once you see it that way, the silence between stars becomes more important than the stars themselves, because what dominates the universe is not what shines, but what doesn't. I sometimes think about how easily our intuition is fooled by scale, how the human mind evolved to judge distance across valleys and oceans, not across light years. And when you look up, you instinctively compress everything into a dome a few kilometers away. because that is what your brain expects. But in reality, those points of light are separated by trillions of kilometers. And beyond them lie trillions more you cannot see. And the sky you thought was crowded is mostly empty space, punctuated by a few nearby neighbors. The unsettling part is not just that the universe is large, but that your direct experience hides that largeness, because what you see feels complete, even though it is barely anything. And once you realize that the familiar comfort of the night sky changes, it no longer feels like a full tapestry overhead. It feels like standing in a dark field with a few distant houses visible, knowing that an entire unseen world extends far beyond the limits of your sight. The easiest way to misunderstand space is to think of it as something you could eventually cross if only you had a faster engine, because our intuition is built on travel, on roads that connect cities, on oceans that can be sailed, on distances that shrink as technology improves. But space does not behave like that. And the moment you start putting real numbers on it, the idea of connection begins to collapse. The moon looks close enough to reach a familiar companion hanging just beyond the atmosphere. Yet it sits about 384,000 kilometers away, far enough to line up 30 Earths between us and it. And even traveling at escape velocity, it takes 3 days to get there, which is already a reminder that the nearest celestial body is not a short trip, but a journey. And that is the first step. The next step is Mars, often described as our neighboring planet, but at its closest, it lies roughly 55 million kilometers away, and at its farthest, more than 400 million, meaning that even light, the fastest thing in the universe, takes between 3 and 21 minutes to travel one way. So, when a rover on Mars sends a signal, it is not a conversation but a delayed exchange. Every command sent into silence, every response arriving long after the moment has passed. And this is still inside our own solar system, still in what we casually call our backyard. I remember once imagining what it would feel like to stand on Mars and look back at Earth, expecting something recognizable, perhaps a blue marble in the sky. But in reality, Earth would appear as a faint point of light, barely distinguishable from the surrounding stars, and everything you have ever known would collapse into that single pixel, not because it is small, but because distance erases detail, and space is almost entirely distance. When we try to leave the solar system, the scale becomes harder to hold on to, because the farthest human-made object, Voyager, launched in 1977, has been traveling for nearly half a century at more than 60,000 kilometers per hour. And despite that relentless motion, it is only about 165 astronomical units from the Sun. Still within the vast region, influenced by our star, and it will take another 300 years just to reach the inner edge of the Oort cloud, and tens of thousands of years to cross it completely, which means that even our fastest machines barely scratch the surface of interstellar space. The nearest star, Proxima Centauri, lays 24 light years away, and at Voyager's speed it would take more than 70,000 years to reach it. Longer than the entire span of recorded human history. And this is not an extreme example. This is the closest possible target, the easiest journey, the first step beyond our system. Meanwhile, our radio signals, the only evidence of our existence that travels at light speed, have been expanding outward for about 125 years, forming a sphere 125 light years in radius. And that sounds impressive until you compare it to the Milky Way's diameter of 100 0.000 light years, at which point our entire technological civilization becomes a microscopic ripple, a whisper that has barely left the neighborhood. There is something sobering about realizing that even if another civilization exists just a few thousand light years away, it has no idea we are here, because our signals have not reached them. And even if they responded instantly, we would not hear back for millennia. And the same is true in reverse, because the galaxy is not just large. It is large in a way that breaks communication, turning every potential neighbor into an isolated island separated by oceans of time. When you extend this beyond the galaxy, the problem becomes absolute, because the Andromeda galaxy is 5 million light years away. And any message sent there would arrive long after the sender's civilization had vanished. Meaning that even if the universe is full of life, the distances alone ensure that each pocket of awareness lives and dies in isolation. Space does not forbid contact through hostility or barriers. It does something quieter and more final. It stretches the gap so wide that interaction becomes meaningless. And the result is not emptiness of matter, but emptiness of connection. A cosmos where everything exists, yet almost nothing can ever meet. When most people imagine the universe, they picture something crowded, galaxies scattered everywhere like glitter across black velvet, stars filling the dark with structure and texture. But that picture is misleading, because what dominates the universe is not the galaxies, but the spaces between them. And once astronomers began mapping the positions of galaxies in 3 dimensions, instead of just projecting them onto the sky, they discovered something unexpected. Not a uniform distribution, not a random scattering, but enormous regions where almost nothing exists at all. One of the most striking examples emerged in the early 1980s when astronomers surveying galaxies near the constellation Boötes plotted their data and found a massive spherical gap, a region roughly 330 million light years across, containing only a few dozen galaxies where thousands should have been. And this became known as the Boötes void, a structure so large that you could line up more than 3,000 Milky Way galaxies across its diameter and still remain inside it. It is difficult to convey how empty this is, because even the word empty suggests absence within something. But the void is not a hole punched in a dense universe. It is closer to the opposite, a vast region where matter never gathered in the first place, where gravity had too little to work with. And over billions of years, that slight deficit amplified until the region became a cosmic desert. There is a thought experiment astronomers sometimes use to make this tangible. If the Milky Way were located at the center of the Boötes void, early astronomers would have looked through their telescopes and seen no other galaxies at all. No Andromeda, no faint spiral nebulae, nothing but isolated stars within our own galaxy. And until the mid-28th century, we might have concluded that the Milky Way was the entire universe. Not because we were mistaken in reasoning, but because the evidence simply would not exist. That idea always unsettles me, because it means the apparent structure of the universe depends on where you happen to be. And our sense of cosmic scale is shaped by accidents of location. The Boötes void is not unique either. It is one example of a pattern that dominates the large-scale structure of the universe, with voids occupying roughly 80% of cosmic volume, while galaxies and clusters cling to thin boundaries between them, forming a foam-like geometry, enormous bubbles of emptiness separated by fragile filaments of matter. Even more strangely, we appear to live inside one of these underdense regions ourselves, sometimes called the KBC void or the local hole, a region of below-average galaxy density spanning billions of light years, meaning that our cosmic neighborhood is quieter than average, more spread out, less crowded, as though we inhabit the outskirts of a vast cosmic city where the lights grow sparse. This is not just poetic imagery. The presence of such a void may even influence our measurements of cosmic expansion, because galaxies inside underdense regions experience gravitational pulls outward toward denser surroundings, subtly altering local motion and potentially contributing to the tension in expansion measurements. But regardless of those implications, the deeper realization comes from understanding how voids formed in the first place, because they trace back to tiny fluctuations in density in the early universe. Variations of 1 part in 100,000, barely perceptible ripples in an almost uniform sea of matter and energy. And over billions of years, gravity amplified those differences, drawing matter into slightly denser regions, while emptier regions lost more and more, a slow redistribution that left behind immense cavities. The universe did not carve out voids later. It allowed them to grow from the beginning, making emptiness the default state and structure. The exception, once you picture this, the cosmos stops looking like a field of galaxies and starts resembling a network stretched across vast bubbles of nothing, where luminous matter occupies thin walls while the majority of volume remains dark and silent. I sometimes try to imagine standing inside one of these voids, far from any galaxy, where the sky would contain only a few faint smudges of distant light and almost no reference points. And what strikes me is not the darkness, but the absence of context, because without nearby galaxies, the universe would appear small, local, and deceptively simple, and you might never suspect the immense structures beyond your horizon. Emptiness does not just dominate the cosmos, it hides the cosmos from itself. And the more you think about that, the more the universe begins to feel less like a crowded expanse and more like scattered islands surrounded by an ocean so large that most of it has never been illuminated at all. Once astronomers realized the universe was dominated by vast voids, the next question became unavoidable. If galaxies are not spread randomly, then what determines where they appear? What invisible logic arranges matter into clusters and leaves other regions nearly empty? And when large-scale surveys began mapping millions of galaxies, the pattern that emerged looked less like scattered points and more like a network. Long filaments stretching across hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, with enormous voids in between, a structure now called the cosmic web. The name sounds poetic, but the geometry is real. And once you see it, it becomes difficult to unsee, because galaxies are not isolated islands drifting independently. They are beads threaded along enormous strands. And those strands themselves connect into a lattice spanning the observable universe. Our own galaxy is not at the center of anything special. It sits on one of these filaments, part of a thin gravitational highway linking clusters far larger than anything visible in the night sky. And for decades, this web existed mainly in simulation. Supercomputers evolving the universe from tiny fluctuations after the Big Bang and consistently producing the same sponge-like architecture, matter flowing into sheets and filaments, voids expanding, clusters forming at intersections. What made this more than theory was the gradual ability to detect the faint gas that lies between galaxies, hydrogen so diffuse it barely emits light, yet spread across millions of light years. And in recent years, astronomers finally captured direct images of these filaments, faint bridges of glowing gas connecting galaxies, confirming that the cosmic web is not just a statistical pattern, but a physical structure through which matter actually flows. It helps to imagine these filaments not as static scaffolding, but as rivers, slowly channeling gas toward the dense nodes where galaxies grow. feeding star formation over billions of years, and even transferring angular momentum, causing chains of galaxies to rotate together, as though entire sections of the universe share a common spin. But the most surprising part of this architecture is that most of it is invisible, because the luminous matter we see, stars and gas and galaxies, accounts for only a small fraction of the total mass shaping the web. The rest is dark matter, a form of matter that does not emit light, does not absorb light, does not interact with electromagnetic radiation at all, yet exerts gravity. And its presence was inferred long before the cosmic web was mapped, when astronomers noticed galaxies rotating too fast for their visible mass and clusters bending light more strongly than expected. Once simulations included dark matter, the cosmic web naturally emerged, because dark matter collapses under gravity first, forming a skeleton into which ordinary matter later falls, meaning the web existed in darkness long before galaxies lit up its structure. This idea shifts the picture completely, because what we call the visible universe becomes a thin, luminous coating on an invisible framework, galaxies tracing the densest parts of something we cannot directly detect. And even that is not the full story, because the expansion of the universe itself is accelerating, driven by what we call dark energy, a component that makes up roughly 68% of the cosmic energy budget, causing space to stretch faster over time, pushing clusters apart while gravity tries to pull matter along the filaments. When you combine these pieces, the cosmic web becomes less like a static structure and more like a dynamic organism. Dark matter forming the bones, baryonic matter forming the glowing tissue, and dark energy stretching the entire system outward, slowly thinning the connections. There is something quietly unsettling about realizing that the architecture of the universe is dominated by ingredients we do not understand. That the visible matter composing stars and planets and everything familiar represents only about 5% of reality, while the rest is inferred indirectly, mapped through its gravitational influence. I sometimes think about how different the universe would appear if we could see dark matter directly. If the sky were filled not with isolated galaxies, but with continuous filaments glowing across immense distances, revealing that we are embedded in a structure far larger and more interconnected than the naked eye suggests. Instead, we see only the brightest knots, like lights along a distant highway, unaware of the roads connecting them. And the deeper you look, the more the universe stops resembling scattered objects and starts resembling an invisible machine, quietly organizing matter on scales so vast that the galaxies themselves become mere details in a structure built mostly from darkness. Let me try something simple with you. Something that begins with the kind of address you might write on an envelope. Except instead of a street and a city, we keep stepping outward layer by layer, until the numbers stop feeling like places and start feeling like abstractions. You are on Earth, a rocky planet, about 700 kilometers across, orbiting an ordinary star we call the Sun, one of hundreds of billions of stars in the Milky Way galaxy. And already this is easy to say but hard to picture, because the Sun feels central only because we are close to it. Yet in the galaxy it sits quietly in a minor spiral arm called the Orion Spur. Not at the center, not at the edge, just somewhere in between, orbiting the galactic core every 230 million years. If you step outward, the solar system becomes a tiny bubble inside the local interstellar cloud, which itself lies within a larger cavity known as the local bubble, a region of hot, thin gas, roughly 1,000 light years across, created by ancient supernova explosions. And that bubble is just a small pocket within the Orion arm, which is itself one of the spiral features of the Milky Way. A barred spiral galaxy, roughly 100,000 light years in diameter, containing perhaps 250 billion stars. When I first tried to visualize this hierarchy, what struck me was how quickly the sense of scale collapses, because each step outward turns the previous one into a point, the Earth into a dot, the solar system into a speck, the Orion arm into a faint streak. The Milky Way itself is not alone either. It belongs to the local group, a gravitationally bound collection of about 100 galaxies spread across roughly 10 million light years, dominated by the Milky Way and Andromeda, which are slowly moving toward each other and will merge billions of years from now in a slow gravitational dance. Beyond that, the local group sits on the outskirts of the Virgo supercluster, a vast assembly of galaxy groups and clusters extending over about 100 million light years. And for a long time, astronomers thought this was the major structure we belonged to, until better mapping revealed something even larger, a gravitational basin now called Laniakea, spanning roughly 520 million light years and containing around 100,000 galaxies, all flowing toward a region known as the Great Attractor. Even this is not the end, because Laniakea itself forms part of an even larger filamentary complex embedded within the cosmic web structures, stretching close to 1 billion light years, thin threads connecting superclusters across immense distances. And at this stage, the word address starts to lose its meaning, because the scale no longer resembles anything human. All of these layers, Earth, Sun, Milky Way, local group, Virgo, Laniakea, the cosmic web filament, sit inside what we call the observable universe, a sphere roughly 93 billion light years across, defined not by a physical boundary, but by how far light has had time to travel since the Big Bang. That number is easy to recite, but impossible to internalize, because it means the light reaching us today from the most distant regions began its journey when the universe was extremely young, and even then, the expansion of space stretched those distances so that the sources are now tens of billions of light years away. What fascinates me about this layered address is how it changes your sense of location, because you are no longer on a planet orbiting a star. You are on a planet inside a system, inside a galaxy, inside a group, inside a supercluster, inside a filament, inside a cosmic web, inside an observable bubble. And each container dwarfs the previous one until the entire hierarchy begins to feel fragile, like a stack of nested shells floating in darkness. Sometimes I imagine writing this full address line by line, knowing that each additional line reduces everything above it to insignificance. And by the time you reach the observable universe, even the Milky Way feels microscopic. The unsettling part is not just that we are small, but that the structure itself has no obvious center, no preferred level, no final step that feels like home. Because every layer is just another region within something larger. And the more carefully you trace the address, the less it feels like a place you inhabit, and the more it feels like a coordinate in a system, far too vast to belong to anyone at all. When we talk about the observable universe, the phrase itself hides something important, because observable does not mean total. It means only the region from which light has had time to reach us since the beginning. And that distinction matters more than it seems, since the observable universe is about 93 billion light years across. Yet the universe itself may be vastly larger, perhaps unimaginably larger, perhaps infinite. The reason comes from geometry, from measurements of the cosmic microwave background that show space is remarkably flat, meaning that over the entire observable region, Parallel lines remain parallel and triangles add to 180 degrees within tiny margins of error. And this flatness implies that what we see is only a small patch of a much larger whole. The way a small section of Earth appears flat, even though the planet is round, except in this case, the curvature is so small that the total universe must extend far beyond what we can detect. Some conservative estimates suggest the universe is at least hundreds of times larger than the observable region. Others, based on inflationary cosmology, push that number to 10, 23 times larger, and in many models it does not stop at large. It becomes infinite, extending without boundary in every direction. I sometimes try to picture this by shrinking the observable universe to something manageable. Imagining all 93 billion light years reduced to the size of a coin, and then realizing that the full universe, under some inflationary estimates, would extend far beyond the scale of galaxies, even in that analogy, turning our entire visible cosmos into a tiny window, a keyhole looking out onto a room we can never enter. The reason we cannot see beyond this keyhole is not technical limitation, but the speed of light and the expansion of space, because regions beyond a certain distance recede faster than light can cross, meaning any signal emitted there will never reach us, no matter how long we wait. This creates a cosmic event horizon, not a wall in space, but a boundary in causality, separating what can influence us from what forever cannot. And beyond that horizon lies not darkness in the ordinary sense, but permanent inaccessibility. The regions of the universe that exist yet can never be observed. If inflation occurred in the early universe, as the evidence suggests, then the implications become even stranger, because inflation is not expected to end everywhere at once. Instead, it may continue indefinitely in distant regions, creating separate pockets where expansion slows and matter forms, each pocket effectively its own universe, disconnected from the others by rapidly expanding space. This leads to the idea of a multiverse, not as science fiction, but as a consequence of the mathematics, a vast ensemble of bubble universe, each potentially with different physical constants, different particle masses, different histories, most of them empty or short-lived, some capable of forming stars and planets, and perhaps a few hosting observers who look up at their own skies and wonder about everything beyond. The unsettling part is not just the size, but the isolation, because even if these other regions exist, they are causally disconnected. No signal can pass between them. No information can bridge the gap, meaning the multiverse, if real, is not a community of universes, but a collection of solitary domains, each forever sealed from the others. Even within our own observable universe, isolation already dominates, because galaxies beyond our local group are gradually slipping beyond reach as expansion accelerates, their light stretching until it fades into invisibility. And in the far future, observers in our galaxy would see only a handful of nearby companions, with no evidence that a vast cosmos once surrounded them. That thought changes how smallness feels, because it is not just that we occupy a tiny place, it is that our tiny place may be all we will ever access, a small island of matter inside an ocean of unreachable existence. Yet there is something paradoxical here, because the same physics that isolates us also allows us to infer what lies beyond, to calculate the geometry of space, to deduce inflation, to imagine regions we will never see. And in doing so, we extend awareness beyond the limits of observation. The universe may be structured to keep its regions apart, but it is not structured to prevent understanding. And the fact that a species on a small planet can reason about horizons it cannot cross suggests that smallness is not just a limitation, but also a vantage point, a place from which the vastness becomes visible in a different way, not through travel, but through thought